Today, I will present our paper, FPRadar, a machine learning approach to systematically detect novel abuse of web APIs for browser fingerprinting. My name is Bahrami, and this is a collaborative work with Umar Iqbal and my advisor Zubair Shafiq. This work focuses on stateless tracking, which is also commonly known as browser fingerprinting. Online tracking can be broadly divided into two categories, stateful and stateless tracking. In stateful tracking, trackers rely on unique and deterministic user identifiers that are typically stored as cookies in the browser. However, mainstream browsers have taken strict actions against tracking cookies, and most of them, with the exception of Chrome, now block them. That crackdown has motivated trackers to move towards a more invasive form of tracking called stateless tracking. Stateless tracking or browser fingerprinting is a tracking technique that does not require trackers to store any identifiers at the client side. Fingerprinters are constructed by combining information from various web APIs, such as combining the phones and languages installed in the browser. However, for a fingerprint to be useful, it needs to be unique and stable. To make the fingerprints more unique, trackers try to incorporate multiple web APIs, including new web APIs over time for browser fingerprinting. From the mitigation perspective, the incorporation of new APIs over time makes fingerprint a moving target, and this has puzzled the browser vendors. In this paper, we try to address this problem by proposing a graph-based machine learning technique that predicts new APIs that trackers might exploit for browser fingerprinting. Let's look at an example about how browser fingerprinting works. In this example, a JavaScript snippet is embedded in a website. Let's imagine three different users visit this website, and the JavaScript code will run on their browser and extract information from several web APIs. For example, the number of processor cores, languages installed, and the screen size of the machine. The values returned by these properties are combined to create a distinguishing identifier at the client side for each user. Trackers gather different information at the client side using different APIs supported in web browsers and then exfiltrate this information to the server. Next, let me little bit talk about some of the issues of existing state-of-the-art browser fingerprinting detection mechanisms. In contrast to cookies, it is not trivial to detect and block fingerprinting. Fingerprinting detection requires sophisticated static and dynamic analysis. Prior work has tried to detect browser fingerprinting manually using manually crafted heuristics. But heuristic has several limitations. Designing a heuristic is laborious and time consuming, and they are brittle. It means that they may miss fingerprinting scripts that do not match their narrowly defined detection criteria. And they don't work for evolved or new APIs because it is predefined based on known fingerprinting techniques. And finally, they reactively looking for known fingerprinting techniques in one point of time. Prior work has also looked at ML-based techniques to detect browser fingerprinting. Such techniques try to detect fingerprinting script based on their structure and execution. These approaches address some of the problems that flummox heuristics, but they're still perfect. Specifically, they automatically learn the tracking behavior from features and they're flexible to minor changes in the script behavior. However, similar to heuristic, they're not designed to detect new or evolved APIs. In summary, existing detection mechanisms are not designed to detect new fingerprinting techniques. We need approaches to detect the abuse of JavaScript APIs for fingerprinting in future. To build this gap, we propose FPRadar. FPRadar is a graph-based approach that leverages the longitudinal connectivity of APIs to predict what API could be abused in fingerprinting in the future. And it consists of four components. I will go through each step in the following. So the first step is input generation and data collection. To longitudinally analyze web APIs, FPRadar needs to measure their usage on the web over time. We rely on the Wayback Machine to access historical snapshots of a script for the last 10 years on the Alexa Top 100K websites. Next, FPRadar relies on principle of guilt by association to detect the abuse of web APIs for browser fingerprinting. It means that if an API is being used alongside known fingerprinting APIs, then we can presume that the API in question may also be used for browser fingerprinting. To model this principle, we represent Web API concurrence in a graph. Let's take a closer look at how this graph works. Before we can link APIs in graph representation, we need to extract them from raw scripts. To extract APIs from a script, we create abstract representation of a script through ASTs. ASTs allows us to create uniform representation of scripts from different developers and get rid of non-essential content like comments. Once we extract APIs from a script, we map them in a graph representation. Specifically, we create a node for each API and add an edge between nodes if they appear in the same script. Then we assign weight to edges based on the frequency and time. And then we extract these nodes from all of the script files for a particular year and build a separate graph for each year starting from 2010 to 2019. We call these graphs longitudinal graphs. Once we create the longitudinal graph representation, we try to predict the abuse of unknown APIs in the future based on their concurrence with fingerprinting APIs. Now let's have a closer look at the graph prediction procedure. First, we try to predict the API concurrence in the future, that is, which API will appear in which script in the future. Suppose we have actual Web API connectivity data from 2010 to 2011, and we want to predict the concurrence in the next year. We rely on graph embeddings and manually extracted features from the graph representation of Web API concurrence to predict the concurrence graph for the next year. And our intuition for relying on these features is that the existing connectivity of APIs is indicative of their future connectivity. We repeat this process and predict the API concurrence over 10 years by iteratively building temporal graphs. Next, we predict which APIs will be used for fingerprinting based on the predicted concurrence graph. The next step is temporal clustering. Here we have our temporal graphs starting from 2010 to 2019. FPRadar non-temporally clustered the graph based on the Leuvian method, which partitioned the graph at each snapshot such that the modularity is maximized between clusters. And then FPRadar links cluster across consecutive years together to form temporal clusters. Specifically, FPRadar links clusters together if their Jacquard similarity is more than a threshold. Now let's take a look at our measurements and results. In total, we extract 14 temporal clusters, and then we try to detect clusters, fingerprinting clusters, based on the percentage of API keywords that are used in the open source Fingerprint.js2 library, and also the fraction of API keywords that appear in fingerprinting scripts to non-fingerprinting scripts. And using this approach, we detect 6 potential fingerprinting clusters, and that the most dominant cluster has a lifespan of 9 years, and the number of keywords in this temporal cluster has like 63% of keywords in temporal cluster has a common keyword with Fingerprint.js2 library, and also the ratio of FP fingerprinting keyword to non-fingerprinting keyword is about 27. We next investigate only the dominant cluster. So in the dominant cluster, we link JavaScript API methods and properties with their parent class. For example, if we observe changing time API keyword, which is a property of battery status API, or plugins, which is a method of navigator API, we know that their parent class is battery status or navigator. We then try to figure out if there is any public resource, including research publication, W3C documentation, or public forums that introduce or implement this keyword in a fingerprinting technique. Depending on the time of our detection using FPRadar in comparison with the disclosure date, we categorize these keywords to on-time detection, early detection, late detection, and for a number of keywords that there isn't any public disclosure, we call them not yet disclosed. The false positive rate of FPRadar might be in question for you, particularly regarding the keyword that we said there isn't any ground truth as far as we know. So for 56% of the keywords, we know that there is a ground truth, and FPRadar detects abuse of these APIs before in 40% of the keywords, FPRadar detects them before disclosure. For 29% of the keywords, FPRadar detects them on time, and for 13% of keywords, FPRadar detects them later than disclosure time. But as we said, for 44% of the keyword, there isn't any comprehensive ground truth. And to demonstrate the validity of these detected keywords, we need to manually analyze the scripts and see how they can be abused for fingerprinting. Now I will introduce a number of our new findings. We have selected a sensor API among our findings to analyze it here. A lot of study has been done about how trackers identify users using sensor information. And these studies date back to 2014, but the point is that all the studies are based on an old interface, such as device motion event and device orientation event. And this interface is able, for example, gather information about the change in motion. And our study also detects these APIs as fingerprinting. But these interfaces are not part of sensor APIs. Sensor APIs is approximately a new API, and it is continuously being updated, and it is supported by Chrome, but not Firefox and Safari. FPRadar detects the use of a number of new features of sensor API, for example, ambient light sensor, which returns the current level of the light around the hosting device, and it is not part of old interface. And as far as we know, it is not publicly disclosed. We have also detected use of other API keywords, including page visibility, a number of API keywords in the web worker, gamepad, and clipboard API. But because of time limitation, I can't go through them, but you can read more about them in our paper. FPRadar's code as well as the data is available online on our GitHub, and we hope that the community will build on it to improve countermeasures against browser fingerprinting. Thank you for listening, and your questions are welcome.